Welcome to Metal Welding Lecture Series by Professor Joyjeet Ghose. This is the 12th lecture of the series. This lecture will be on ultrasonic welding, USW. He will be discussing about ultrasonic welding principle, ultrasonic plastic welding versus metal welding. Ultrasonic welding setup is also discussed. Ultrasonic welding components like press, nest or anvil, transducer, booster, sonotrode, horn is also discussed. Metallurgy of ultrasonic welding, wedge reed system and lateral drive system, ultrasonic welding variables are also discussed. Advantages, limitations and applications of ultrasonic welding are also discussed, so do not miss and watch the full video. For the next video in the lecture series, please click the suggested video link above. You may also click on the playlist at end of the video to access all the videos. Please subscribe this channel and yes, do not forget to like and share. Also click on the bell icon to receive instant information of new videos uploaded. Thank you.
Hello friends, welcome to this lecture 12 on ultrasonic welding. This is one of the lecture of a series of lecture on metal welding processes. In this lecture, we will be discussing the details of ultrasonic welding. So let's start. So before we start discussing about ultrasonic welding, what is ultrasonic? Ultrasonic is basically a sound wave which has a frequency of above 16 kilohertz. In ultrasonic welding, we use sound wave in the range of 20 kilohertz to around 40 kilohertz. For metal, we require the higher frequencies for welding, maybe around 30 to 40 kilohertz. And for other non-materials, we can use ultrasonic frequency in the range of 20 kilohertz. So ultrasonic welding is not only used for welding of plastics or polymers, it can be used for welding of metals, and it can be used for welding of dissimilar metals, metals to plastics, plastics to metals, and different metals to different metals, aluminum to copper. So different metals and different polymers can be welded by ultrasonic welding. So the system slightly varies for plastic and that for metal. So what we'll be discussing, our main discussion will be focused about metal ultrasonic welding rather than plastic ultrasonic welding. So the figure that you see in front of you is basically a metal ultrasonic welding, which is called wedge reed system. The figure A is a wedge reed system where it is used for metal ultrasonic welding. So I'll be discussing about the details, construction and all these things in subsequent slides. So let's start here. So first, salient points about the ultrasonic welding I'll be discussing. So here the heat generated is less, and it is generated by interfacial friction of the faying surface. Now how this friction is created? This friction is created by the ultrasonic vibration, and the heat generated is very less, and there is no melting takes place. The heat generated is less and there is no melting takes place, particularly in case of metal ultrasonic welding. In plastic ultrasonic welding, slight amount of melting can take place, but in metal ultrasonic welding no melting takes place, and therefore the welding is carried out in solid state. Therefore it is called a solid state welding. No filler material is added. We do not add any kind of filler material. The temperature that is generated in the interface between the two metals or two metal piece of work piece we are joining is about 30 to 50% of the melting temperature. So it does not melt, and the heat affected zone is also less. The residual stresses are less. The distortions are less. Can be used for joining dissimilar materials, preferred for lap joints or overlap joints where the two metal pieces are overlapping. And here we apply a compressive load which is static in nature. A continuous compressive load is applied, and dynamic shear load is applied by means of a ultrasonic vibrations in transverse ultrasonic vibrations, which is basically a dynamic shear dynamic load, and because of that we obtain plastic flow of materials. And these are the salient features of ultrasonic welding. I again repeat some of the very important points. The heat generated is less, and it is generated because of interfacial friction, and this interfacial friction of the faying surface, the two surfaces that we are joining. And how this interfacial friction is created? This interfacial friction is created by ultrasonic vibrations in the transverse direction. So because the heat generated is less, so no melting takes place, particularly in case of metal ultrasonic welding, and we do not add any kind of filler material. and therefore it is also an autogeneous welding process, and we obtain a true metallurgical bond. The heat generated is less, and therefore the temperature rise is around maximum. It can go up to 50% of the melting point, so it does not melt. The heat affected zone is obviously very less, and therefore since heat affected zone is less, the residual stress is also less, the distortions are also less. It can be used for welding dissimilar materials like copper, aluminum, or metal, or plastics, and preferably it is carried out for overlapping joints. And here we apply a compressive load which is static in nature. A continuous compressive load is applied, and in form of transverse ultrasonic vibration we apply a shear load which is dynamic in nature. So under this static compressive load and the shear load, the interface of friction occurs, and the friction raises the temperature, and the load, the compressive load completes the weld. So it's a solid state welding process. In two workpieces are bonded by pressure exerted by to the welding part, combined with the application of high frequency acoustic vibrations, that is ultrasonic. What is the frequency? Frequency ranges from 20 to around 40. To be realistic, it is around 20 to 40 kilohertz. It can go up to around 70 kilohertz. Also, the welding time is very less. It can vary from 0.5 to 1 second or maybe less. So since there is no melting, it is carried out in solid state. It is called a solid state welding, and it is also, you can say, an autogeneous welding process. No additional filler material is added, no fluxes, no sealing gases, etc., etc. Now here one important thing is the vibratory action of the ultrasonic welding breaks up and disperses the moisture, oxides, and the coatings or any other coatings that is there, and normally only degreasing may be required for cleaning. Okay, so brief history. It was developed by basically the first patent was assigned to Robert Soloff and Seymour Lindsay. Soloff was working in a company called Branson Instrument. In Branson Instrument, he was doing something with ultrasonic welding and plastic films. He has said that he has seen the ultrasonic probe welded the plastic films when accidentally he has touched it, and he realized that ultrasonics can be used for welding of plastics. And Soloff founded a company called Sonics and Materials Incorporated, and the first patent was awarded to Soloff and his colleague Seymour Lindsay. So this is how ultrasonic developed, and later on it is developed, modified for metals welding also. So you can visit ultrasonic welding, which is basically a website of a company called Sonitech. So plastic versus metal. In plastic, in metal, what happens? The vibrations are transmitted to the workpiece in transverse direction. I'll show you here in figure. So here the two workpieces are here, and this is the sonotrode tip, and the vibrations are given. This is a lateral drive system. In lateral drive system, the vibrations are given in this lateral directions, ultrasonic vibrations, and static load is applied in this direction. Okay, so applied static load, and this is the transverse vibratory directions, and heat is generated here, and it is welded. How it is welded, the metallurgy will be discussing later. Whereas here the vibration in longitudinal directions, that creates the melting, and welding is completed. This is mainly used for plastic welding. This is for this type of mode of welding is for metallic welding. It may be a lateral drive system like this, or it may be a wedge reed drive like the one we have seen in the first slide. Yes, this is a wedge reed system. So there is a reed and a wedge, and therefore it's called wedge reed system. This is a mass clamping force which applied the compressive load, and this is the booster. So this is the booster transducer which produces. Transducer is what? Transducer basically converts the high frequency alternating current into a mechanical vibration. This mechanical vibrations is amplified by an amplifier and ultimately pressed onto the sonotrode tip, which is moving in this direction. So the vibration is pressed on transverse direction, and there is a sonotrode tip has a gripping surface. It grips the top plate and vibrates in this direction. So I hope this I have a figure here. So gripping surface, I'll show you later the gripping surface. So here this has a gripping surface. The gripping surface grips the top surface, and it vibrates like this. So when it vibrates like this, something happens metallurgically. The phenomena is not yet very clear, but we have a practical hunch to it, and which we'll be discussing. However, this is the mechanical vibrations. Basically, transducers are those uses some piezoelectric material. This piezoelectric material, when you press a alternating current which is of high frequency, during one half of the cycle it contracts and the other half it expands. So this contraction and expansion has high frequency, but the amplitude is less. So that is basically we are converting the electrical energy into a mechanical vibrations using these transducers, and amplitude being less, we use an amplifier which is called basically a booster, and this is pressed onto this reed. The reed is applying a compressive load, and this is coupled here. I'll show you actual figure here, then you will understand the actual picture, you will understand how it is coupled here, and then this load is applied here. So there is a compressive load which is acting, and there is a transverse shear load that is taking place. So compressive as well as transverse shears like this. So because of that, because of the friction here, so initially the contact surface between the two metal pieces will be less because of the asperities. Now as the friction moves on, the asperities will be abraded, and the area of contact will also increase. The area of contact increases, and two metal surfaces come very close to each other. When the two metal surfaces comes very close to each other, and because of the heat, what happens, atoms from one metal diffuses to other metal, and atoms from other metal diffuses to the other metal, and simultaneously crystals starts recrystallization takes place, and because of the recrystallization a metallic interlocking takes place. So this will be shown in the next slide here. Okay, before that, what are the components here? I'll come to that later on. The anvil and the tip are made of high speed steel because it will be under tremendous amount of friction, so that the wear is less. So ultrasonic welding can be spot, seam, line, ring, etc. depending on the tip. Okay, so what are the components? You have a press which applies a static compressive pressure. You have a nest and anvil on which the two metal pieces are placed, and the ultrasonic stack consists of the booster and the sonotrode, that is horn, and the transducers. So these are there, and the converter basically what it does is that converts the electrical signal into mechanical vibrations, and the booster modifies the amplitude of the vibrations that increase the amplitude. We require a higher amplitude, and sonotrode applies the mechanical vibration to the parts to be welded. And we have an electronic ultrasonic generator, which is the power supply, which is basically high frequency alternating current, and we have a controller to control the movement of the press and delivery of the ultrasonic energy. So this is the basic components that is required. So what actually happens here, due to vibrations, the oils and oxides are dispersed from the interface. Any kind of coating also is dispersed if the metal pieces have any kind of coating. And what happens, there is asperities, so the asperities will be in contact with each other, and due to the rubbing action, due to the friction, the asperities will be abraded and metal will come, the area of contact will also increase. As the area of contact increases, the heat generated will be more, and atoms will try to diffuse. Simultaneously there will be recrystallization that is taking place, and because of the recrystallization you have a actually metallic bond. True metallic bond is true metallurgical bond, we call it, that is obtained. Again, the metallurgy of this is not completely clear to everybody. People are taking an intelligent guess or a realistic guess depending on seeing the microstructure like this. You can see the microstructure here, and you can see there's interlapping. If you this figure is of same material, if you see dissimilar material, you can see true interlapping that is taking place, or interlocking that is taking place, and you can even the seam is very difficult to identify because of the recrystallization takes place. You can see the crystal size are smaller here, so recrystallization has taken place here, and the seam is very difficult to identify even in high magnification. So an excellent weld is obtained. So under static pressure, it converts the electrical vibration energy into a friction work and deformation energy and limited temperature right between the workpiece and the interface. Now this instantly activates the atoms in the welding area of the workpiece and enable mutual penetration. So this is diffusion that is taking place, and ultimately achieving a solid connection between the weldment. So this already I have discussed. in a diagram. So this is very important. Two things are happening: recrystallization and diffusion. These two things are very important. So here atoms are diffusing as well as recrystallization, and because of that interlocking takes place. So this is how a lateral drive system. In lateral drive system, you have this kind of thing. This is the booster, and this is the sonotrode tip is connected here, and the load is applied by this only, and this is the anvil on which the workpiece is placed. And this is the gripping surface. Very important. You do not want the slippage between the sonotrode tip and the workpiece. Otherwise, what will happen? Friction will always also will happen between the sonotrode tip and the workpiece, and heat will generate, and it will lead to sticking of the sonotrode tip to the workpiece. This is also sometimes it do happen between the workpiece and the sonotrode tip. So we provide a gripping surface to the tip so that it does not slip and does not stick. So this is the wedge reed system, where you have reed, the weight is transferred, the mass is transferred in this manner, the compressive load is applied in this manner, and here we have a lateral drive system, the compressive load is applied in this manner. So both this figure you can see the coupling. This is the coupling here. The vibration is in this transverse direction, made in transverse direction. The time taken for welding is very less, and here the load is applied here and vibration will be lateral drive system. The figure I have taken from Sonomond Ultrasonic Incorporated. You can visit their website. They have large number of equipments. You can see the equipment specification. So this is a lateral drive system. So this is a roller type for carrying out seam ultrasonic welding. So the important parameters are clamping force, how much force is applied. Okay, this is very important. Is that how much force we should apply, and how much what should be the frequency. Okay, so that is very important and that will depend on what is the thickness of the material, what is the hardness of the material. So basically you want material to flow, so hardness, more the ductile, more easy it is for ultrasonic welding. That is one parameter that is very important. The more the ductile, that is why copper and aluminum are very easy to weld in ultrasonic welding. And very often welding between copper and aluminum ultrasonic welding is preferred. So again, clamping force, you do not want to apply high clamping force. That will create problem, that will lead to sticking. Also, you do not want to give too low a clamping force. So adequate clamping force is required, and that will decided based on the thickness of the workpiece and the hardness of the workpiece. So also the power required, what should be the frequency of vibrations. So, and the time, exposure time is also important. So vibration amplitude and tooling, all these things are very important parameter in ultrasonic welding. Okay, application from computer electronic industries to aerospace to automotive industries to plastic industries, medical industries, packaging industries, and many of you will be aware of this. This has ultrasonic welding. Okay, and your automotive car key, if you have a car key, the plastic is welded to the, normally it is welded to the metal key by ultrasonic welding. It takes very less amount of time. So car key, your bike key, scooty key, all these are ultrasonic welded. Dissimilar metal can be welded. This is the advantage of ultrasonic welding. Low deformation, residual stress is very less, high quality weld is obtained. It can be automated, skill required is very less. You don't require skills. Basically, you have to place it properly and press a lever, and ultrasonic welding will be completed within less than a second probably. So we will be able to weld thick to thin plates. Excellent for aluminum, copper, already I have discussed. Oxides, etc. will be automatically dispersed. Ultrasonic welding was one of the fastest method of joining. No foreign substance as a filler is required for ultrasonic welding, and it is considered to be an autogenous welding. Spot seam welding can be carried out. Surface damage is minimum, and cleaning, it is a clean joining process. So no arc, no fumes, nothing. So it's considered to be a very, very clean joining process. So limitations also, it is restricted mainly to overlap joints or lap joints. Only small and thin parts can be welded. Thick parts are difficult to weld. Thick to thick is difficult to weld. Thin to thick you can join. easily. Thick to thin is difficult to weld, and thick to thick is very difficult to weld. So workpiece and equipment are may fatigue because of this ultrasonic load. Fatigue can take place, and workpiece sometimes may get bonded to the anvil as well as to the sonotrode tip. So that is the limitations of ultrasonic welding. Okay, so that's it in this lecture. Thank you for watching this. In the next lecture, we'll be discussing about electroslag welding. Thank you once again for watching this video.